All right, this is video 23 for the behavioral analysis series, and I'm going to be continuing where I left off as far as doing the two examples of showing discontinuity. The first function, or first example, is using Dershowitz discontinuity function, where it's discontinuous everywhere, and that was where it was defined to be 1 for rational numbers x and 0 for irrational numbers x, and we proved that it was discontinuous everywhere. Now this example was the second one, and you're given the set A where it's the set of x where x is greater than 0. Define h of x to be 0 for the irrational x's in A. Define h of x to be 1 over n for if x is of the form m divided by n, where m and n have no common factors other than 1. And then last, define h of 0 to be 1. So this function is not continuous for the rationals values in the set as far as the rationals being in reduced form of m divided by n. So claim 1 will show h of x is not continuous at c equals m over n. And again, m divided by n, that's going to be in reduced form. So no common factors other than 1. So we know the irrationals are dense in the reals. So since the irrationals are dense in the reals, then for any neighborhood around our value c, since it's a real number, that neighborhood is going to contain irrational numbers. So let's find a sequence, call it xk, where xk is irrational for all of the members of the sequence. So for all indices k as a natural number. So we're going to pick all of the irrational values that are around our value c in some neighborhood, have it as a sequence, call it xk. So xk is a member, so each xk is a member of the neighborhood of 1 over k around c, where you take c out, so they can't be c itself. C is a rational number, so we only want irrational xk values. So to puncture neighborhood around c, so the 1 over k neighborhood around c. So this means we have this sequence xk converging to c, and we know that based on our definition, the function is defined to be 0 for irrational values. So each xk value, it's going to equal 0 when you plug it into the function. Hence, we have a sequence such that xk converges to c, and so since f of xk equals 0 for all members of our sequence, then f of xk converges to 0, but that's not equal to 1 over n, and 1 over n is the value you get when you plug in c into the function, because remember, c is a rational number, so h of x is equal to 1 over n. So we produced a sequence where it converges to c, but the function, the sequence of f of xk's, does not converge to f of c. So therefore, our function is not continuous for the rationals. And I was using the letter f here. It should be h. It should be h of xk. And yeah, so that's pretty much identical almost to the example in the last video. You just use the fact that the irrationals are dense, so therefore you can form a sequence of irrational x's where the x's converge to some value c, where you want the value c to be rational, so that when you plug the irrational values into the function, you get 0, and so that sequence f of xk converges to 0, and that's not equal to 1 over n, and 1 over n is the value for when you plug in c into the function. So it's got to equal f of c for it to be continuous. All right, and then I was using f, and then where it should have been using h. All right, so that part isn't tricky. It's the second claim where I claim that the function is continuous, actually is continuous for irrational value c. So here's a sketch, and I'm going to go through the thought process before I go into the proof. So what does it mean to be continuous? H of x is continuous at c if and only if for all epsilon there exists a delta, so that for all x and a, we have the absolute value of the difference of x minus c less than delta, implies that the absolute value of the difference of h of x minus h of c is less than epsilon. All right, that's what it means for it to be continuous. Well, we know for all irrational values x, it's certainly going to be that because h of x is 0 for all irrational values x. So for all irrational x, we know that since, well, c is irrational, so when you do x minus c less than delta, that's definitely going to imply h of x minus h of c is less than epsilon, since h of x is 0, h of c is 0. So 0 is definitely less than any real number epsilon. So for irrationals that are close to c, it's fine. It's pretty obvious it's going to be continuous if c is irrational. Now, it's when we have rational values of x, and how do we handle that? Where the rational values of x are of the form x equals m over n. And again, m over n is in reduced form. Well, by Archimedean principle, we know there exists a capital N where 1 over capital N is less than epsilon. So there exists a capital N, so 1 over capital N is less than epsilon by Archimedean principle. So we know that. So we need to show that in some region around C, all the x values, where x is these rational values, m over n, are such that we get the absolute value of h over x is less than, which is less than or equal to h over x, which is less than 1 over capital N and less than epsilon. Now I wrote it as the absolute value of just h of x because c is irrational, so h of c is 0. So h of x minus h of c is really just h of x. So somehow I need to incorporate this capital N so that I get it to be, so for some region around C, we have the x values so that when you plug them in, the h of x is going to be less than this 1 over n, capital N, which is going to be less than epsilon. All right, so that's the thought process, the logic. Now it's going to be, how do I go about formally doing this? Now, first note that if you have any real numbers a and b such that 0 is less than or equal to a less than b, and you're given some capital N star as a natural number, there are only finitely many rational numbers x in the open interval a, b, where x equals this m over n in lowest terms. And rational, there's finitely many rationals x in that, such that you have 0 less than n less than or equal to capital N star. In other words, there's going to be finitely many rational values x whose denominator is going to be less than capital N, less than or equal to capital N. It might seem a little bit obvious, but I just kind of did a little mini proof to show that. And why that is, let x be in a, b. So that means a is less than x, less than b. Then we have a less than m over divided by n less than b, multiplying by n. We get an less than m less than bn. So m is an integer, and it's bounded in this range of a times n and b times n. So there can only be finitely many possibilities for m in this range an, comma, parentheses an, comma, bn. And that's with the condition that m and n share no common factors but 1. Since n is a natural number, and there are only finitely many of these, because we're assuming we're going to have 0 less than n less than or equal to capital N star. And n star, that's a finite value. So there's going to be finitely many that come before it. Thus, there are finitely many rationals for which x equals m divided by n in the open interval ab under the condition that we have 0 less than n less than or equal to capital N star, where n star is a natural number. In other words, we've just shown that for any open interval ab, where a is 0 is less than or equal to a less than b, there are only finitely many rational numbers whose denominator is going to be less than or equal to this capital N star as a denominator. All right, so since we have a equals the set of x's where x is greater than 0 and h of x is defined on a union 0, then for ab, as far as being part of a union 0, where a is less than b, there will be finitely many x's in the any open interval ab such that the denominators little n is going to be less than or equal to the denominator capital N. So finitely many rationals that have this in some open interval ab, part of our, that's going to be where a and b are part of our a union 0 domain, such that the rationals, there's going to be finitely many of them whose denominator is less than or equal to capital N. All right, and like I said, it was kind of sort of obvious, but I did this orange thing as a justification in case it wasn't obvious. So since that's true for any AB, let's focus our attention on some region around C. Say we have the regions C minus 1 and C plus 1. So what we're going to do is we're going to try to ignore these finitely many rationals, x equals m over n, and the interval c minus 1, c plus 1, whose denominator n is less than or equal to capital N for some capital N in the natural numbers. That way we'll focus on only the x values whose denominators are little n bigger than capital N. Okay, so, and that's going to be, since it's going to be infinitely many as you get shrinking as far as the fraction values, the denominator gets larger and larger, infinitely larger, it's shrinking to 0. So there's going to be infinitely many rationals in that case where the little n is bigger than capital N. So just to visualize, I drew this. So you have the open interval c minus 1 to c plus 1. So you obviously have c in the center. The blue dash marks, those are going to be the x's with denominators that are less than or equal to capital N. All right, and these are going to be farther away from c than the x's with denominators bigger than capital N. All right, because of these blue dash marks, these are going to be bigger numbers. So the farther along either to the right of C or farther along to the left of C than those with the smaller denominators, since they would be closer to C for the smaller denominators. So those are the blue dash marks, those are the x's with denominators less than or equal to capital N. So what we're going to do is find the value x star in yellow, find the one that's closest to C. All right, so find the one that's closest to C, and then let delta be the distance from C to this x star value. Then we can form an interval C plus delta or C minus delta so that the x's that are within this interval are going to be the x's with denominators that are going to be bigger than capital N. All right, so hopefully that makes sense. So we first take an interval C minus 1, C plus 1, shrink it down to C minus delta, C plus delta, and focus only on the where that interval does not have any rationals with denominators less than or equal to capital N. So that's what we're going to try to do. So then for x's in that open shrunken down open interval c minus delta c plus delta. As n goes to infinity, we know that m is fixed, and n is going to get infinitely large, and x equals m over n goes to 0. So we need to find capital N. So for all little n bigger than capital N, for all the irrationals that's in this delta neighborhood around c. So the absolute value of x minus c less than delta implies that the absolute value of h of x, right, because h of x minus h of c is going to equal just h of x, because h of c is 0, since c is irrational, and our function evaluated for irrationals is 0, so it's just h of x. So then the absolute value of h of x, and we know our function for rational values x is going to be 1 over n. So even if we do have irrationals or rationals, they're always going to be less than or equal to 1 over n. And then since n is bigger than capital N, then 1 over n is less than 1 over capital N, and then that's going to be less than epsilon. All right, so that's the thought process. I probably went a little bit too descriptive, but here's the actual proof. So the proof of the second claim was to show that h of x is continuous for all x's in A, where x is irrational. So let C be a rational number in A. Given epsilon, by Archimedean principle, there exists a capital N, so that for all 1 over capital N, so that there exists a capital N, so that 1 over capital N is less than epsilon. So for the interval c minus 1, c plus 1, there are only a finite number of rationals with denominators less than n, right? Because recall that x is, we're focusing on the x's, that's equal to m over n in reduced form. So there's going to be finite amount of rationals with denominators less than capital N in this interval. So we can choose delta as small as we like, so that c minus delta, c plus delta contains no rationals with denominators smaller than capital N. So then it follows that for all x in A, we have that the absolute value of x minus c less than delta implies that the absolute value of h of x minus h of c is less than or equal to the absolute value of h of x. H of c is 0, and then this is less than or equal to 1 over n, and that's going to be less than 1 over capital N, which is less than epsilon for all little n bigger than capital N. So thus, h of x is continuous only for the irrationals in A. All right, so the proof itself wasn't too long. I just wanted to explain how the proof came about, and hopefully that made sense. That was an example that I needed to do and clarify in the last video. So what's presented now are just more theorems. We're still dealing with continuity. Now we're going to focus on like absolute max, absolute min, boundedness, and those kind of things. So for continuity over closed interval, closed and bounded intervals. So if a sequence xn, so it's a subset of the closed interval AB, and xn converges to x, then x has to be in AB, the closed interval AB. It's closed and bounded. Theorem. So this is just saying the same thing. It just says if all n in capital N, sorry, all natural numbers n where a is less than or equal to xn, which is less than or equal to b, then a is less than or equal to the limit of xn, which is less than or equal to b. Note that if, let's say you had an half open interval, so it's open around 0 and closed around 1, you could have the sequence 1 over n is in that interval. But the limit of this, as n goes to infinity, is 0. And 0 is not an element of that interval 0 to 1, where 0 is open, and then a parentheses around 0 and bracket around 1. So it's required that you have a closed and bounded interval for the limit to be part of that interval. So a function f has an absolute max over a if and only if for all x in a, f of x is less than or equal to f of x star for some x star, and then x star may or may not be in a. That's the definition for f to have an absolute max. Now, a theorem, and then you could do a similar definition for absolute min. So a theorem, if you have the function f going from I to the reals for I is closed and bounded interval a, b, and this function is going to be continuous, and f attains its absolute max min over a, b. And then the next thing is we'll go over two lemmas. Lemma 1, if you have continuous function of the closed interval a, b to the reals, then the function is going to be bounded over that closed interval a, b. All right, so to prove this, I'm doing a proof by contradiction. So let's suppose f is not bounded on the closed interval a, b. So what does it mean to be unbounded? That means for all little n bigger than capital N, where capital N is a natural number, there exists some sequence xn in AB, the closed interval AB, where the absolute value of f of xn is greater than n. All right, so that's what it means to be unbounded. And since we're assuming f is not bounded, there's going to be a sequence xn and the closed interval AB. But since the sequence xn is in the closed interval AB, xn is bounded. Now we don't know is if it converges or not. So it may converge, it may not converge for this sequence xn. But we know by Bolzano-Weierstrass theorem, for any sequence bounded, there's going to be a convergent subsequence. So there exists a convergent subsequence x and k, where x and k, let's say, converges to some number x. So x and k's in our closed interval AB, and since it's in that, that means the limit x is also in the closed interval AB. But f is continuous on I, so x and k, the sequence converges to x, then f of x and k converges to f of x. But we know a convergent sequence must be bounded. This is a contradiction because for this subsequence x and k, which is a subsequence of xn, and this xn is some sequence in AB, where f of xn, absolute value that's greater than n, for all little n bigger than capital N. So that means f of absolute value of f of x and k is going to be greater than nk for all little nk bigger than k in the natural numbers. So that means f of the sequence of f of x and k's is not bounded. But yet we know that sequence converges, and since it converges, it must be bounded. So we've just established that in fact it's not bounded. So since it's not bounded, then it would mean that the subsequence of x and k does not converge. Contradiction, right? Because we already said that there's that is a convergent subsequence. So therefore, f must be bounded. Okay, so that's the proof of the lemma 1. Here's lemma 2. If you have a function f from the closed interval AB, which is calling it I to the reals, F is continuous, then you have, and there exists some X star where the star is as the subscript or superscript. So there exists this X star with the star as a superscript in AB, where F of X star is equal to the supremum of the set of F of X's for X's in the closed interval AB. And that supremum is going to be greater than or equal to F of X. Similar thing for the, there's going to be a X star, but this time it's as a subscript. And so where this is going to be equal to the infimum of the set of F of X's, that's going to be less than or equal to F of X. All right, so for this lemma, I'm going to prove the first one. I'll leave that as an exercise for you to prove the second one. So proof of one. Okay, well, we know by lemma one that we just proved F is going to be bounded over AB, right? Because F is continuous. So by lemma one, since the set of F of X's, F of X values, where X is an element of AB, that's bounded. So we know it's bounded, and since it's bounded, then we know the real numbers has the least upper bound property, so the supremum of this set must exist. Due to completeness of the reals. All right, so since the supremum exists, let's call it Y star. All right, so we're calling it Y star. And so what we need to do, we need to show there exists an X star in AB where when you evaluate F of X star, that's equal to Y star. Right, that's what we need to show, right? Because that's got to be the supremum. All right, so consider Y star minus 1 over n. So you're going to be a little bit below this supremum. All right, and I guess, so there's going to be some f of x in, so this is going to be y stars minus 1 over n is going to be less than some f of x in. And since we're dealing with 1 over n, so it's going to be this sequence for all little n bigger than capital N. Since this is not an upper bound. Okay, so we know that, and this gives us a sequence of f of xn's part of our set of f of x's, and then x is part of closed interval AB. So this gives us a sequence part of that set, as well as a corresponding xn being a sequence of AB. Hence, our sequence xn is bounded. And so by Bolzano-Weierstrass theorem, there's a convergent subsequence. So let's say there exists a x and k of xn, which converges so x and k. Let's say it's going to converge, and also it converges to x star. So by sequential criterion continuity, f of x and k converges to f of x star. All right, so I claim that y star is equal to f of x star. So I got to prove that claim. And once I've proved that claim, I'm pretty much done, because I've shown there exists this x star where that's going to be the function evaluated at that. It's going to be the supremum, which is going to be greater than or equal to f of x for all x's in AB. All right, so we need to show that we want the difference of y star, absolute value, the difference of y star and f of x star to be less than epsilon if they're going to be equal to each other. So we need to show that for all epsilon, absolute value of y star minus f of x star is less than epsilon. Well, we know, so note, we know y star minus 1 over n is less than f of xn. So that's, we can rearrange this. So that implies that y star minus f of xn is less than 1 over n. All right, so because we established that earlier, because y star minus 1 over n is not an upper bound, so that means there's got to be some x that's bigger than it, that it might possibly be the supremum, but we let that be a sequence of values of f of xn. Okay, so we can have okay, so we have that the absolute value of y star minus f of xn or sorry, y star minus f of x star is equal to, if we add and subtract, if we add 0 essentially, so is y star minus f of x in k plus f of x in k, which is, and then minus f of x star. So we just added 0. That's going to be less than or equal to, by triangle inequality, so this. Okay, so that's what we have, and we need, this whole thing needs to be less than epsilon. This needs to be less than epsilon. All right, so what can we use? Well, we already know this part, so x and k converges to x star, so then by sequential criterion we have that. So we know by continuity, or we can make this as small as we like. Well, since you're adding one component to another component, you need the whole thing to add up to epsilon. We're going to make it so that it's epsilon over 2. So that's going to be less than epsilon over 2. So we can make this as small as we like. So let's say make that less than epsilon over 2, which means we want to make the other thing to be less than epsilon over 2. So how do we make this less than epsilon over 2? Well, we know that this right here, that's going to be less than 1 over n, and we can make that, by Archimedean principle, be less than epsilon over 2 if we find the correct value n. So essentially we're going to make this less than 1 over nk, and then that 1 over nk is going to be less than epsilon over 2. So then we have that going to be epsilon over 2 plus epsilon over 2, which is epsilon. All right, so that's how we're going to go about it. So let's first handle the 1 over nk thing. Okay, so find, let's call it nk prime, where 1 over nk prime is less than epsilon over 2, or nk prime greater than 2 over epsilon by Archimedean principle. Okay, so we'll use that for the first thing. Now for the other one, see, so we're going to choose nk double prime to be such that the absolute value of the difference of f of x in k minus f of x star to be less than epsilon over 2. And we can do this, right, because since we already know that the f of x in k converges to f of x star, so it's going to be for all in k, so it would be definitely true for f of x in k double prime converges to f of x star. Or it could just, because we know that's convergence. Okay, so now we're going to pick in k to be the maximum of these two, nk prime and nk double prime. All right, so then we have absolute value of y star minus f of x star. That's going to be less than or equal to y star minus f of x in k. And then plus absolute value of f of x in k minus f of x star. All right, just like what we had up here. And then this is going to be less than 1 over nk. And then plus this is less than epsilon over 2. And since 1 over nk that's going to be less than epsilon, then this is all going to be less than epsilon, or sorry, less than epsilon over 2. So less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Okay, so then therefore y star is equal to f of x star. All right, so that's the proof for the first one, where there exists an x star in the closed interval AB, where f of x star is the supremum of the f of x values. Just to quickly go over it, since that set of f of x's is bounded, the supremum exists because of completeness of the reals. Let's call the supremum y star. We need to show there exists an x star in AB where f of x star equals y star. So consider y star minus 1 over n. It's a little bit below the supremum. Then we have y star minus 1 over n less than f of x n for all little n bigger than capital N, since y minus 1 over n is not an upper bound. This gives a sequence of f of x n in the set of f of x values, as well as a sequence xn in the closed interval AB. But we know the sequence xn is bounded, so by Boson and Weierstrass theorem, there exists a convergent subsequence. So let's say this convergent subsequence x and k converges to x star. By sequential criterion for continuity, then we have f of x in k converges to f of x star. And so the claim is y star equals this f of x star. And that's what we need to show for all epsilon. The absolute value of the difference between the two is less than epsilon. So since y star is minus 1 over n is less than f of x n, then that implies y star minus f of x n is less than 1 over n. And so we have that when you take the absolute value of y star minus f of x star, you add 0 in the form of minus f of x in k plus f of x in k. Then apply the triangle inequality so that you have y star minus f of x in k plus the absolute value of f of x in k minus f of x star. Well, we know the convergence of f of x in k to x star, so therefore we can manipulate the second thing to make it as small as we like, since it's true for all epsilon, so make it epsilon over 2. Then for the first thing, the y star minus f of x in k, well, since y star minus f of x in is less than 1 over n, then y star minus f of x in k is going to be less than 1 over nk. And then we want 1 over nk to be less than epsilon over 2, so we add the two together to get epsilon. So that's why I said find nk prime, where 1 over nk prime is less than epsilon over 2, where nk prime itself is greater than 2 over epsilon, guaranteed by the Archimedean principle. Choose nk double prime to be such that you have the second thing being less than epsilon over 2 due to the convergence of f of x and k convergent to f of x star. Amongst the two, nk prime and n double prime, or nk prime and nk double prime, we choose the max. And that's where we get the proof to finish. All right, so that's where I'll stop it for this video.